So welcome back, um, and hope you had a chance to go through the notes. So in the last lecture and this one also, the idea is to discuss causality and essentially the geometry of space-time. And while we give examples in our examples, we often use Minkowski because it's something we can understand. But the whole point is to sort of go beyond Minkowski space-time and make rules for how we study general relativity in general space-times. And one of the rules which we're going to discuss today is what type of space-times we're supposed to discuss at all. Now, it's a subject of certain amount of dissent because these rules don't literally follow from GR. They have to be added to GR to make it, in some sense, tractable or doable. And well, as we always do in physics, we make up some provisional rules. We work with them. If they don't look good, eventually we may give them up or modify them. So we are working with some provisional rules. It's very important for students, particularly, to understand that things that we do when the subject is still in some state of discovery is to make things define things provisionally, and still in our mind we must allow that different people would define them differently, and we must keep those different definitions in our mind at the same time. So it requires a lot of care. Now, what did we discuss last time? We talked about chronological past and future of a point. We talked about causal past and future of a point, and the causal diamond. And then we then we defined this, we stated a theorem about convex normal neighborhoods. And that theorem basically tells us that although a manifold M might not admit for connecting points by geodesics or for points to be reachable by geodesics, there'll be some small neighborhood of any point which does allow for that. It's the only place, I believe, so far where I mentioned geodesics. So when I talk about a path, I'm not assuming in general that a path is a geodesic. Therefore, it need not be a path that a particle can follow. Okay, but a geodesic is a path that a particle follows. It's the path that extremizes the length and or the interval. And just because you can get to a path in the future or past in a causal way or in a chronological way doesn't guarantee that a geodesic will get there. Okay, I should have said, of course, geodesic is the path followed by a free particle, a particle that's just placed into a space-time and allowed to, with some initial, let's say, position and velocity, and allowed to go. Of course, by firing rockets, which happens all the time in GR when we discuss different kinds of situations, we keep firing imaginary rockets, then of course you can go on other kinds of paths. But geodesics are special. So geodesics will become more and more important, and they are at the heart of the Raychaudhuri equations. But as I said, you should be very careful that I haven't been talking about them so far, except in the context of convex normal neighborhoods. Now, the last thing, and those will come back several times. Now, the last thing we did last time was to talk about a-chronal sets and to talk about future endpoints, future or past endpoints of a curve, and future or past extendable or inextendable curves. And I think this went pretty well, and I think you must have got the idea. There's one thing I didn't probably have time to point out, at least I can't remember pointing it out, which is that a-chronal is a little bit subtle. What is subtle about a-chronal is the following. It basically says that there are no pairs of time-like separated points. Now, the reason for this is going to be important. We are going to be looking for something to be an initial value surface uh, in order to define solutions of Einstein equations. Now let's look at Minkowski, our favorite example. And here is X, here is T. So this surface is a-chronal. And you can very well see that, this is what we want. I mean, we want to define initial data on a surface looking like the wavy line I just drew. But actually, this surface is also a-chronal by what I just said, just along the light cone, also a-chronal, because it's not, no points are time-like separated on it, right? If I take 2 points, then they are null separated along that. So they are not time-like separated. So it's also a-chronal. But the surprising thing is that this is not equivalent to saying that the surface is space-like or is everywhere space-like or null. In Minkowski space, it is equivalent, but in general, it's not. You would think that we could just say, instead of that word a-chronal, we could just say surface is space-like or null. Okay, but that's not enough for the following reason. Space-like or null tells us basically about the connection of the nature of tangent vectors, and you can have a surface where the tangent vectors are everywhere, say space-like, but it's still not a-chronal. And this can happen if I have an interesting topology. So imagine that my space-time still has a Minkowski metric, but the space is a circle. So X actually goes from 0 to 2 pi r. Okay, and time still goes upwards. Oops, my lines are getting worse. Time still goes upwards. Okay, now you see this statement about being space-like or null is basically a statement about the slope of a curve. So this is 1 plus 1d, just an example. And the metric is Minkowski, though the space is not, space-time is not because of this compact circle. Now imagine I have a curve which goes like this and then goes behind this cylinder, a helix basically. I hope you can see clearly what I have in mind. So it wraps around the cylinder. Now you see the way I've drawn it, it's always space-like. It's everywhere space-like because the tangent vector is sloping at less than 45 degrees. Sorry, and that's what space-like means. However, there's no problem finding a time-like path which connects 2 points on this. I simply start here and I go there. This is time-like path, time-like path. So you see that in this case, just saying that the surface should be space-like doesn't make it a-chronal. This is not a-chronal. This particular line in 1D, just a simple example, but you can make bigger, higher dimensional examples. So this line is not a-chronal. Okay. That's why a-chronal requires a slightly stronger wording than just saying space-like or not. Okay, I hope that point is clear. Extendable was, I think, pretty clear. And with both of these things, we now have the crucial definition, which is going to help us understand GR on generic manifolds. And that is the definition of a Cauchy hypersurface. Hyper is somewhat unnecessary word, but it's used because we don't know what dimension we don't know a priori. Finally, it's going to be codimension 1. Usually in mathematics, surface means something of real dimension 2. Here it could be in 3 plus 1D, a Cauchy hypersurface would be of real dimension 3. Okay, so what is it? It's a-chronal. So it's an a-chronal. Now there's one more thing, and I'm going to write it first. Space-like surface such that. Now remember, 2 minutes ago, I basically said that just being space-like doesn't make you a-chronal. But of course, to be a-chronal, in particular, you have to be space-like or null. If you have any time-like segment in your surface, then it can't be a-chronal. So if I just say a-chronal, then the local condition on tangent vectors is space-like or null. And many authors, including Wald, leave it at that. But Witten added space-like. And I'm going to go with that because it's a little more intuitive, and we could add back the null possibility at a later stage if we want. So this is the provisional definition. So it's a-chronal, and in particular, everywhere space-like, never even null, certainly never time-like. But it has one more property, and it's that extra property which makes it Cauchy. And the property is that every inextendable curve through a point P in the manifold. So I'll call the surface capital sigma. So sigma I'll use when it's Cauchy. If I just use S, then it'll be something more general. It's convenient. So every point P that's in M, but P is not in sigma. So every inextendable curve through P that's in M, but not in sigma, passes through sigma. And let's immediately see a picture of this. So here's my M. Now, I'm not assuming Minkowski or anything. This is a general definition, but I can't draw general manifolds. So this is my sigma. I've drawn it to look space-like, okay? But it has this property that if this is P, then I draw past I draw a causal path through P. So that path can be either time-like or null at every point. That's what causal means. And it's also inextendable. In particular, here I'll draw it backward in time to be past inextendable. It's inextendable in both directions. And my statement is that it better pass through sigma. If I try drawing another one, it'll also pass through sigma. If I draw another one, it'll also pass through sigma. If I draw one that's null, absolutely null, assuming that's 45 degrees, it still passes through sigma. Basically, anything you do going causally into the past on an inextendable curve, because remember, if I didn't say inextendable, it might have ended somewhere. It might just have ended here and it wouldn't have passed through sigma, but we don't count those. We say if it's inextendable and I'm going into the past, it will pass through sigma. Likewise, I could always have taken, I didn't say P has to be in the future of sigma. It could also have been in the past. And likewise, if P is here instead, then its future inextendable causal curves will all necessarily pass through sigma. Okay, what could happen if a space-time, if a surface is not a Cauchy surface, is that one of these inextendable curves might pass around it in some sense, or just might not pass near it, or we don't know. I mean, so this is a requirement. There are plenty of examples of non-Cauchy hypersurfaces. So this is the definition. Are there any questions about this definition? Let me zoom in. Let me show it to you here. Yeah. Any questions? Okay, good. Clear enough. So this is a Cauchy surface. This has to be for every point P. Yes, yes. Through every P. Thank you. Thank you, Sambit. Absolutely. It has to be for every point P, and that's crucial. Absolutely. Now, there's an immediate sort of corollary or corollary definition, which follows, which says, and this is easy, a globally hyperbolic space-time M is one which has a Cauchy hypersurface. So if you can find even one Cauchy hypersurface, you call the space-time globally hyperbolic. Okay, now it may look like just asking for one Cauchy hypersurface is too little, but as we'll see in a few minutes, if you have one, you have infinitely many. So it can be proved. So one is enough. One is enough to require, and then you get more. Okay, now why did we do all this? Well, I hope compared with the last lecture, this starts to become a little more intuitive about where the physics is going to come from. We do this because then we can, so as I've written in my notes, it sets the stage for physics for an initial, okay, for us to specify initial conditions and determine the future. And of course, classical physics is deterministic, and classical physics is always based on the fact that you need to specify initial conditions, and then the future is determined. This is true whether it is simple classical mechanics problems or simple classical field problems, Klein-Gordon field, Dirac field, it doesn't matter. It's subtle in the case of gauge fields, but after proper gauge fixing, it's also true there. Okay. Now, one thing to realize, and it's obvious from the picture, is that this Cauchy surface sigma actually divides, sigma divides the space-time into a past and a future. Okay, I think it's pretty obvious because from the definition, the past is defined as the place from where future-directed inextendable causal paths pass through the surface, and the future is the place from where past-directed ones do the same thing. Okay. Now, a couple of points. First of all, Wald said it nicely. In a globally hyperbolic space-time, the entire future and past history of the universe can be predicted or retrodicted from conditions at the instant of time represented by sigma. Okay. And here Wald may be slightly inconsistent with his own definition because he's allowed sigma to be null, and a null surface can't be thought of as at an instant of time. It can be an instant of some null time. But since I've taken it space-like, Wald's statement is literally true. Okay. So any questions? A missing point type inextensible curve through P might end before sigma. Absolutely. Then sigma is not a Cauchy surface, and that manifold is not globally hyperbolic because of its missing point. Thank you, Rahul. You said it exactly right. So the key point here is that the absence of the non-existence of a Cauchy surface is going to be a bad property of a manifold. We're just going to refuse to deal with such manifolds. Is that point clear? So that's the whole idea. So the manifold with one point deleted has been killed off by defining globally hyperbolic. So it's not possible for such a manifold to be globally hyperbolic. Also note an amusing thing, since you just made that point. The sigma that Shreyansh, everything is in the notes. You'll have to, I'm not going to be able to repeat everything that I say. I'll try, but I'm not necessarily be able to repeat it immediately because it interrupts the flow. In fact, the flow got interrupted. Yeah, I was making a point that once you delete a point, it's not just that the sigma I drew fails to be a Cauchy hypersurface, but that you can't find any sigma which will be a Cauchy hypersurface. Put it in the future of that point, then future directed geodesics from before that point will run into trouble. Put it in the past of the point, then past directed geodesics from the future of the, or not geodesics, I should have never said that, causal curves from the future of that point will run into trouble. The key point is when we delete points, we get inextendable curves, which nevertheless end before getting to the Cauchy surface. Okay, and this is the problem. So exactly this is why we don't like, yeah, that point is like a stone, all right, if you like. I like to think of it as a hole in space-time, which actually, as I mentioned last time, is a part of space-time which vanishes at one morning and reappears a few seconds later. And that's exactly your problem. If you send out a signal and you're hoping that your signal will reach the moon, then if on the way a point in space-time vanishes while your signal is still trying to reach the moon, then your signal not only cannot reach the moon, but it gets completely stuck. It doesn't have anywhere to go. Okay, the signal is a freely propagating photon, and we don't even know what to make of a photon when it reaches a point which isn't there. So it's more than a stone. It's really something missing for a small period. Okay, it would be easier if I knew it was missing for all time, maybe, but here it's just, you can delete a point, then it's just missing for an instant. Yeah. So Farman, you're right. We can specify initial data on a null surface and evolve as a series of null surfaces. We can do that. And in fact, in QFT, without gravity, something like light cone gauge or light cone coordinates implicitly try to do that, just that we are not going to do that now. My only excuse is that I'm to a large extent following Witten's exposition, though not very literally. So just if you want to allow it, just allow it, just add it there. Okay, good. Okay, now one interesting point is that a Cauchy surface sigma is necessarily closed. And this can be proved. And let me just here make a comment about, so first of all, so Witten has given a proof that it's closed, and I might want to give that proof also at some point, but not right now. But I do want to say something about the meaning of closed, and so this is a small digression. I did ask you to read whatever, some reference, maybe my book or something else, to find out what limit points, closed, compact, and all that mean. And we'll use all of them. But just now we are not using compact, we're only using closed, which is simpler. And let me just state it for you once so that you understand it. First of all, let me state it for a very generic topological space. So a topological space. Now, I may end up, I am going to use the same terminology for topological space as for a manifold, because the only topological spaces we ever are going to consider in these lectures are manifolds. But here you should realize that it's more general. A topological space, take such a space and a subset S, any subset whatsoever. A point P in S is, sorry, a point, this is exactly wrong. A point P in M is a limit point of S if every open set containing P intersects S. The intersection here always means non-trivial intersection. That means if an open set contains P, it necessarily contains also at least one point of S. Now, of course, this is trivial if P happens to be inside S. So let's look at the cases. So here's my topological space. Here's S, and there are three possibilities for P. P is here. P is here. And the third and most interesting one, which is that P is here. Okay. Now, if P, looking at the first example, P is clearly not a limit point. This is S, this is M. P is clearly not a limit point of S because I can surely find an open set like this around P, which doesn't intersect with S. So done. So in the first case, P is not a limit point. In the second case, an open set around P, in fact, for small enough sets, lies inside S. So P is definitely a limit point. Even if you take a huge open set around P, obviously that intersects S. It always intersects S because P itself is in S. So here, it's not a limit point. Here it is a limit point. What about the last case, which is subtle? Well, now we have to ask, drawing this thing, the way I've drawn it, it's not clear whether P is in S or P is not in S. If S, for example, was of the form like this, all points, just an example, all points in the plane such that mod X is less than 1, and P was on the boundary of this with mod X equals 1, then P is not in S. Okay. The other case could have been that S was of this form. It's just drawn the same way. And P is still here. But S is the set mod X less than or equal to 1. Sorry, P is not in S here, and P is in S here. Okay. So you see, these are two different things. The first one is open disk. These are just examples. The definition I already gave you. I'm just trying to exemplify it. This is a closed disk. These are familiar words for such things. Now, in the second case, P is in S. So there's nothing, once it's in S, there's no need to ask if it's a limit point. It is a limit point. A limit point. The non-trivial case is this one. This one. P is not in S. P is on the boundary of S. S is the space mod X less than 1. It doesn't contain all these points. However, the whole setup of P and S is in the manifold M, and now I have to draw an open set of M that encloses P. Now, any open set I draw, however small, overlaps with S. And this shows that P is a limit point, even though it's not in S. And this is sort of the key of this argument, that despite not being in S, it is sort of so close in some sense, not in a metric sense, in a topological sense, that any open set containing P has to contain some other points of S. Okay, if you try to make your open set just the point P, then unfortunately that isn't an open set. That's exactly the point. So it's M with the usual topology. Individual points are not open sets, and the rest follows. So that defines limit point. Okay. Now, now it's easy to define closed. Closed is a set that contains all its limit points. There are other definitions of closed in topology, for example, as the complement of an open set, but it's the same, it's equivalent. It can be proved to be equivalent. So once and for all, we've defined for this course what is a closed set. It's a set that contains its limit points, and limit points are such points that if I enclose them in open sets of my underlying topological space, they always intersect with the set. Is that good? Is this the same as saying P is in the boundary of S? Okay, so in some sense, it helps us to define the boundary. Without these kind of definitions, I wouldn't know how to define the boundary. And one definition of, in fact, the definition of boundary of a topological space is that it's the closure minus the interior. Okay, so boundary of a topological space. Now, for manifolds, a different definition is given, but it's, I think, equivalent enough for us. Okay, boundary of a, sorry, not of a topological space, but of a set in a topological space. A set in a topological space M is defined as S bar minus int of S. So the bar, it means closure. So closure is obvious from what I said. I told you that a closed set contains its limit points, but some sets are not closed. And I showed you an example. This one here doesn't contain its limit points. So the closure is obtained by taking that set which doesn't contain its limit points and adding its limit points. Now it's closed. Okay. The closure of an open disk, not very surprisingly, is the closed disk. Okay. So that defines S bar. Interior is also defined. There's a way to define interior, which I forgot just now, but you can look it up in my book. It's something quite standard about, again, enclosing points. And I think, yeah, I think interior is the set of points such that, yeah, it's very easy to define actually, is the set of points such that I can find open sets around it fully contained in S. Okay, can enclose in open set U that is fully contained in S. And you can see that again from this picture. If P is like this here, then you see that this open set around it is fully contained in S. But if P is here, then regardless whether this is in the manifold or not, as long as P is, regardless of whether this point P is in the set S or not, the fact is that any open set around it isn't fully contained in this. Okay, so the interior of both the open disk and the closed disk are the open disk, is the open disk. This is an example, but this is a general theorem. Okay, so the closure minus the interior is the boundary. So there you have a nice little theorem. Okay, end of digression on on closed. Compact is a little harder and we'll come back to it. We need that also, but I don't think I've used that word so far. And if I do, please catch me. I'll define it. Probably my plan is at the start of the Friday of the next lecture on Friday, which is also when we are going to start getting into some physics. Okay, are we good? Any questions? Okay, then I can continue. Okay. Good. Now, a very interesting fact is that these are properties of Cauchy surfaces, and inextendable causal paths from P. Of course, we said it has to intersect a Cauchy surface, but the question we can ask it is, does it intersect the Cauchy surface more than once? Okay, but answer is it can't. So an inextendable causal path from P can only intersect a Cauchy surface sigma exactly once. If it doesn't intersect, then sigma is not a Cauchy surface. If it intersects more than once, then that's not possible. Let's try to, this is a theorem or a result. How do we prove it? It's actually a very trivial proof. So let's draw this Cauchy surface and let's draw an inextendable causal path, which, okay, It's difficult to actually draw, but let's imagine that the path sort of does that. Okay. Now, obviously, from just drawing the path that I've just drawn is obviously not causal. Okay, because it is space-like in some regions. But let's assume that there's some topology we don't know about, and that somehow the light cones are such that this path still is causal, manages to be causal throughout. Okay. The problem is that this path has a segment which starts on the Cauchy surface and ends on the Cauchy surface, this segment, okay? And it's causal by assumption. But the Cauchy surface is a-chronal, which means no causal path can connect any 2 points, okay? So it contradicts a-chronality. Okay, is this result clear? Why sigma was closed? What is the okay? So I think it will become clearer when I prove that sigma is closed, but we are assuming that we have been given a space-time with what is called the usual topology. And usual topology, okay, so actually good. So you're right. Probably I didn't say enough about the topology of space-time. Good. So actually, the correct statement, of course, locally we know the topology. Locally, it's that of Euclidean space. But I think the correct statement is that for any topology of spacetime consistent with the spacetime being globally hyperbolic. Okay, so the theorem is that sigma, a Cauchy surface, is necessarily closed. Okay, now you would say this is also contradictory because yeah, no, that's fine. I think a space-time which has a Cauchy surface, any topology consistent with that space-time, the Cauchy surface is closed. And I didn't prove it. I left it for proof in the future. Okay. If you want the proof, I've cited Witten's proof of it, and you can look it up right away. Witten, page 18. From the definition he proved. So, by the way, when I say Witten, I always mean Witten's review article, Light Rays, etc. It has light rays in the title. And if you go to page 18, Cauchy, yeah, okay. In fact, I will prove it maybe later in this lecture. Let's come back to that, and please let me know. Let me know. And will his proof hold when? Good question, Krishna. This is for you to figure out. I don't know the answer. Witten nowhere discusses the. Okay, so here's an interesting fact since you brought it up. Witten nowhere discusses null Cauchy surfaces because he assumes they are space-like. His justification is also rather curious, and maybe I didn't appreciate it fully. He says in a footnote, So he says to implement causality in GR, we require S to be a space-like hypersurface. Footnote, more generally, one can define initial data on a hypersurface that has some null portions as long as it is a-chronal. We will consider only the more intuitive case of a space-like hypersurface. So I actually can't tell you more right now, and I haven't had time to think whether everything I'm saying is true in the null case, but you can try and work it out. As far as the proof, as I said, for the space-like Cauchy surface, I will give you the proof either later today or beginning of tomorrow. Mohammed, no, conformal completion I haven't discussed, and I don't know why we need it. I certainly won't use it for the proof that Cauchy surface is closed. Give me a minute and we'll get to those things. Okay, very good. So, so this is what we wanted to say about globally hyperbolic, and we gave a nice property that the Cauchy surface sigma gets intersected by an inextendable path exactly once, not more, not less. Now, this leads actually to a very beautiful result, which we'll come to in 5 minutes. Okay, now let's try to, okay, so now one important question. Supposing I say my surface, I have a surface that's a-chronal and space-like, so far so good, but it's not Cauchy, okay? One example that somebody brought up was we'll take a manifold with a point removed, and then there won't be any Cauchy surface. But actually, we can find an example where there's a good manifold, it's actual Minkowski space, and we pick a surface which is a-chronal, but it's not Cauchy. That's a nice example. So let's ask the question and answer it by giving an example. Are there a-chronal surfaces that are not Cauchy in a globally? So I'll be using this acronym. GHS is globally hyperbolic spacetime. See, if it's not globally hyperbolic, then nothing is Cauchy. So that's not interesting. But nobody said that every a-chronal surface in globally hyperbolic spacetime is Cauchy. We said there's one. I'm going to show you that there are many, but that certainly doesn't say that anything a-chronal is necessarily Cauchy. So let's look at an example. This comes from this I got from Witten, but it's actually quite simple to construct. And as usual, we always fall back on our good friend Minkowski spacetime. And what we'll do is to draw this hyperboloid. Okay. And this I should have really drawn it in a different color. This one. Okay. And you can obviously see what I've drawn. It's basically the past hyperboloid. Okay, and it's defined by saying that x squared plus r squared is equal to t squared. Okay, now from this equation, it's very easy to see that dx by dt, this is in Minkowski. This is an example in Minkowski. Now, dx by dt, you can calculate, and you find that it's just t over square root of t squared minus r squared, and this therefore is always greater than 1 for any t. Okay, so it's space-like. And it's in particular, if it's space-like, it's also a-chronal, because the other thing then you need to only add to this is that there are no time-like curves connecting any 2 points on it. But you can easily see that because you can see all points of this. Pick one point here, pick one point here. There's no chance this is going to be time-like because already this thing is space-like, and any point joining, any line joining 2 points is under it, so it's even more space-like. Okay, so no, so it's perfectly a-chronal, but it's not Cauchy. And how do we see that? Well, we draw a curve that asymptotes. Okay, so we draw a curve that, now again, let me, now that I've got into fancy colors, we'll draw a curve which is like this, coming like this. And then, oh, this software is trying to correct my drawing. Okay, sorry, excuse me. And it bends here and goes null. Okay, so I'm not drawing it well, but it's supposed to tangent to this light cone eventually. So it approaches this light cone, which is a null line. Okay, so this red curve is, of course, causal. Causal simply means time-like or null. In the upper part, it's time-like. In the lower part, it's null. It's not space-like ever. And it doesn't even actually become null. I can make such a curve which is very close, which is time-like and asymptoting to become null. But you see that it doesn't intersect. So the red curve doesn't intersect. The red curve doesn't intersect the yellow curve. So the yellow curve isn't a Cauchy hypersurface because the red curve is an inextendable causal curve and it's not intersecting this one. Okay, so that's my example, which shows why the inextendable curve intersecting the Cauchy, the surface, is an important requirement to be Cauchy. So S is not Cauchy. This S. Okay, so that's an example. Good. Now, We talked about causal futures and causal. Sorry,
could I interrupt for the question?
please, please.
I mean, I was just wondering why such a complicated surface was necessary. Couldn't you just take, say, Tx plane and take x greater than or equal to 0? Wouldn't that be space like a-chronal but not Cauchy?
Tx plane and take x greater than 0. Yeah, but it would have
the line on the real axis with x.
Yeah,
greater.
but it would be a half line, right?
Right. Yeah.
Yeah. So now actually there's a story, and you can look it up in World, about surfaces having edges or not having edges. So yeah, obviously that's certainly not Cauchy. The half line is obviously not Cauchy. But you could just say that, well, it was really the line, and I childishly cut off half of it, and that made it not Cauchy. But with this surface, you see that it's an honest surface extended as far as it will go. It has no end, so it's edgeless. So it's a better example.
I see. Okay.
I mean, because we're trying to find an initial value surface, and the key point is that this one isn't an initial value surface, because if you look in its future, it's not going to be able to predict everything that can happen, and that's really the problem. Okay, good. Okay, so we talked about causal and chronological futures and pasts, and now we are going to talk about domains of dependence. And this is going to be fairly easy, given all we've done, but it's also very important, and it should not be, it should not be very difficult to follow the definition. Okay, so the future, let's write the definition and illustrate it. Future domain of dependence of an a-chronal. Again, I'm taking space-like set S, denoted D plus of S, is the set of all P in the manifold such that all past inextendable paths through P intersect, pass through S. So what I'm saying here is the following. It's actually very closely related to things we already understand. Supposing I take an S that's not a Cauchy surface, like this one I just showed you, this one. Okay. Well, it has some future domain of dependence, the set of all points from which past inextendable paths do pass through it. Right now, I am a little puzzled what that is, but I think it's just this, right? Can someone tell me? Is that, I haven't thought this through, but this, from here, I'm pretty sure all causal paths to the past pass through the hyperboloid, right? If they are here or here, then they don't have to, because they can asymptote this way or this way. So the future domain of dependence of S is only this much. People agree? Okay, good. I think that's correct. So what we are saying is, okay, if it's a Cauchy surface, then its future domain of dependence is exactly all the future. Okay, but if it's not a Cauchy surface, it still has a domain of dependence, which is not the whole manifold. And that's what the concept of future domain of dependence is. And of course, D minus S is the past domain of dependence, defined exactly the same way. And we can take the union of the two. The full domain of dependence, D of S, is D plus of S, union D minus of S. That's the domain of dependence. So domain of dependence is associated to any set. That could even be a single point, or it could be any subset of M. And of course, now we see that in this language, a Cauchy surface sigma is one for which d of sigma is equal to m. But in general, for a general surface S, d of S is a subset of M. And that's why we talk about it. So it's like, for some reason, I'm stuck. I have some surface inside M. I didn't pick a Cauchy surface, but maybe it's a surface that I like. Maybe I want to do something with it. Maybe it's the surface of my house or something. And I want to know what, or of my lab, and I want to know what events I can influence in the future, or what events in the past could have influenced me. And that's the domain of dependence. Clear? Okay. It does rely on future and past inextendable curves, and it relies on the set being a-chronal, and also for me at least space-like, but I think it's okay to take it null. Okay. Now, there's an interesting theorem, which is quite easy to prove actually. So in general, d of S need not be closed. So just in time, we went into the question what closed means, but we can consider its closure. This doesn't have a separate name. It's d of S bar, the closure of the domain of dependence. You're free to consider it. And we have a theorem described by Wald, proposition 8.3.2. I've given the reference in the notes. A point P, given an S, given a a-chronal set S, a point P lies in the closure of D of S if and only if every past inextendable. You know, when I type my notes, I have a little macro for all of these things. We keep typing these words over and over again. Globally hyperbolic spacetime, past inextendable curve. Okay. Every past inextendable curve through P intersects S. What is the content of this theorem? Well, domain of dependence is that something is, there's one, sorry, I think there's one time, sorry, exactly, time-like. If I didn't say time-like, of course, that would be just the definition of domain of dependence. The statement is that if I have the closure, that means I take the domain of dependence and add everything that's on the boundary of it roughly, and include that, then I'm in DS whole barred. Then even every past inextendable time-like curve through P will intersect S, and this is an if and only if condition. So if I find that there's a point such that relative to a a-chronal surface S, such that every past inextendable time-like curve is intersecting S, then I can say, well, P is in the closure of the domain of dependence on S, of S. Good. Now, it's good that I defined closure. Now let's look at some properties of the boundary of this closure. Okay, so this is another theorem. The boundary of the closure ds bar denoted del d of s bar is called a Cauchy horizon. the definition. It's just a terminology, and it's denoted H of S. Okay, so for any set S, we have already defined I plus and minus of S, J plus and minus of S, D plus and minus of S, and now H, which also splits into H plus and minus of S. I'm not going to write here what they mean. It's obvious. It's H plus if it's if it's the part of the boundary of the closure in the future, and if it's that part in the past, then it's H minus. Okay. And why do we define a Cauchy horizon? Well, let's give the statement. It gives us so the Cauchy horizon has a separating property. It separates points P for which S effectively behaves like a Cauchy surface from those for which it doesn't. So in some sense, yeah, exactly. Just what I've said. I don't think I can repeat it any better. It acts as a separator between those places where for which you can think of S as predicting data there, and those parts of the manifold for which you can't. And I can't do any better than show you back this figure. And you see here that we realized that this stuff is the future domain of dependence of my yellow hyperboloid, right? So if I'm in that red shaded region, then I'm in D of S. Now, this light cone, sorry, the light cone, this one is the closure or is the boundary of D of S for this S. Okay, because how far can you go before getting out of the domain of where S can predict things? Well, you can go arbitrarily close to this light cone. So the light cone is the boundary. And exactly that boundary of the closure of the domain of dependence of S is the Cauchy horizon. So in this case, the Cauchy horizon is exactly the light cone. Okay, so the light cone, past light cone, has separated my full space-time, which goes into 4 quadrants, as you can see, 1, 2, 3, 4 quadrants. It's separated, or you can separate it into quadrants along these. Then only this quadrant is the part that you can predict starting with data on S. So it's a Cauchy horizon for S. Was that clear? Closure of, I think I just did that. Yeah, maybe the question is 4 minutes old. Krishna, have I done it? Okay, thanks. Can't I use multiple non-Cauchy surfaces? Yeah. Well, Sambit, that's a nice idea. I could use multiple non-Cauchy surfaces whose future domain of dependence unions to give the manifold. But in that case, why not take the union of those multiple non-Cauchy surfaces and call them a Cauchy surface? Each of them is a-chronal, each of them is space-like. Now, maybe there's some weird situation where we need to do that. I'm not sure, but I'm not aware of such a thing being done. If you know an example, it could be interesting. Okay, there were some questions that I didn't see probably. So often when I'm looking at notes, I'm not looking at your questions. D of P is light cone. I don't remember what that statement was about. Anyway, domain of dependence of a point is the interior of the light cone.
Hello?
Yeah.
Yeah. So in this example, what would be the future and past Cauchy horizon?
By the way, I said something. Sorry, what was the question?
In this example, what would be
Hmm.
the future and past Cauchy horizon?
Good. So, very good, very good. So definitely, I think this is the future Cauchy horizon, and I'm guessing that there isn't a past Cauchy horizon. Because to the past of this surface, everything is okay, right? The surface extends all the way. So maybe this example has only a future and no past Cauchy horizon. But now I got suddenly a panic attack. So give me a second. Did I have to say future domain of dependence? Let me just check the definitions. Is cause? Yeah, it should. I should have said cause. Did I write causal? Sometimes I forget to write the important word, and this is not forgivable. And you should catch me. You should have. Okay. Yeah, causal. Shubhankar asked whether it can be a definition of Cauchy surface. Yes, absolutely. So one can do the whole presentation the other way. First, define domain of dependence of a surface, and then say a Cauchy surface is one whose domain of dependence is all of them. Yes, absolutely. Draw a picture. Yes. Yeah. Okay. Yeah. So Pawan made a comment, and I think he's referring to this idea of some bit that we can use multiple Cauchy surfaces. And the point is that they may not be a-chronal. They are all individually a-chronal, but they may not be a-chronal with respect to each other. And that would not be a good thing, because in that case, it might be that both of them, both of these components of your multi-component system could predict different contradictory data in the future. And then what is the actual? There should be unique behavior of the dynamical variables in the future. So that could, yeah. So yeah, you can consider hyperboloids on 4 quadrants of the light cone, absolutely. And actually, you also can see where this is going. Finally, Rindler space is an example of something where these kind of ideas are certainly going to show up. Good. Okay. Good. Then I said all that. Now there are a few more things, and I have a good amount, 15 minutes before we go to the question period. And this time, I'm going to talk about some nice properties of GHS, globally hyperbolic spacetimes. Okay. So one, we actually proved a theorem on the way, but we didn't notice it. No closed causal paths. A globally hyperbolic spacetime has no closed causal paths, neither null nor time-like. And why? It's the same reason which we gave to explain that the inextendable curve can only meet the Cauchy surface exactly once. The reason was that if it meets, if there's a closed time-like curve, for example, then of course that curve, being an inextendable curve, has to meet the Cauchy surface once, but now it's closed time-like, so it has to come back and then it will meet the Cauchy surface again and again and again and again. So it contradicts my theorem that it meets the Cauchy surface only once. Okay. And that in turn was because any segment of it from the Cauchy surface back to the Cauchy surface contradicts a-chronality, even from a point back to itself. If it's a causal path from a point back to itself, that already contradicts a-chronality. So no closed time-like curves, no closed causal curves, even better. And this is a big deal. All the all these weird paradoxes of going back and killing your grandparent or whatever come from having closed time-like curves, and they are great in science fiction, but they're not great for having predictive physics system. Very good. Okay. Now another one, very nice one, is that any two Cauchy surfaces can be continuously deformed to each other. And a lot of fun comes from this. So here's a Cauchy surface. So let's draw Cauchy surface sigma, and someone else draws a different Cauchy surface sigma prime. So the claim is that I can just take the upper one and move it smoothly without any singularity or breaking or anything, and until it coincides with the lower one. Well, I won't give you the proof. The proof is, again, a precise proof is there in written, but I can give you the idea, and it's very simple and pretty idea. Take any point on this Cauchy surface. Well, take an inextendable causal curve from this. It intersects this Cauchy surface once and only once, as we've just proved. Now take another point on this. Take an inextendable causal curve. It will intersect once and only once. So not necessarily straight or parallel, but absolutely smoothly, you set up a family of curves that are all causal and therefore preserve the properties of sigma prime as you deform it. And now once you have this family of curves, you have a way to smoothly move sigma prime along those curves. So there are some kind of integral curves of a vector field, and Witten sets that up very precisely. Okay, and so this shows that any two Cauchy surfaces can be continuously deformed to each other. Okay. There's a corollary of this, which again Witten has explained nicely. Even a portion, if sigma is Cauchy and S is S prime, I'll call S prime because it is what I called sigma prime before, but now I'm allowing it not to be Cauchy, is a-chronal, not necessarily Cauchy. Then S prime must be homeomorphic, or let's just call it topologically equivalent to a portion of sigma. So what does this corollary say? I think if I draw one picture, you will understand. This is sigma again, but now let me take S prime not to be Cauchy, and let me just take it to be a circle. Now you see, this circle is not topologically inequivalent to this sigma, which I've drawn as a line. I'm just imagining a special case. And you see that there's no subset of sigma that S prime can be mapped onto smoothly, because S prime is compact and sigma is non-compact, just intuitively. One is a circle, one is a line. You can't map a circle smoothly as a subset of a line. Okay, so then that means that this therefore this is not possible. If it were possible, if there was any a-chronal S prime, it has to be topologically equivalent to a portion of any other Cauchy surface. This is not possible. That means that if sigma is, e.g., non-compact but connected, then no a-chronal surface can be compact. So there are consequences. This theorem gives us all kinds of nice results. That, okay, can there be two intersecting Cauchy surfaces which can be deformed into each other? No, I believe not. I leave it for you to look at as an exercise, but I believe that this congruence or this equivalence along time-like curves precisely maps, allows you to deform one to the other. If you actually intersect one with the other, you will get a contradiction. Now, you can find out on your own what the contradiction is, and if it doesn't emerge, I'll talk about it next time. Can't we map the compact a-chronal surface to a closed portion of the Cauchy surface? Sambit, I think not. I think this figure makes it clear, right? So this is a compact, this is by hypothesis a compact a-chronal surface. Okay. The Cauchy surface is this line where it doesn't have any closed portion. Okay, it can't have a closed portion. It can either be compact or it can be non-compact, but it can't have a closed portion, right? So that's the point. So we actually rule out possible a-chronal surfaces by this nice theorem. Please do go to Witten's notes. I think there are a lot of things I'm not doing, but at least whatever things I am doing from his notes, I think you'll find them clearer now that we've talked about them. Okay, now some more corollaries. Okay, so this is, let's see, properties of GHS. 1, 2 is the continuous deformation. Then 3 is this. Then property 4 is in a globally hyperbolic spacetime. J plus of P is closed for all P. And I'll prove it, not probably, almost certainly in the next lecture, for the reason that it will fall out as a corollary of some other theorem, which is a subtle theorem on compactness, and which I'm going to tackle at the beginning of the next lecture. Okay, so right now just take it as a corollary without proof. Next lecture. Okay, one more corollary. M, the whole manifold, is topologically sigma cross R. So sigma is a Cauchy surface, any Cauchy surface, because they are also topologically equivalent. And this is the real line. And you can sort of see the line of proof is exactly the same as this one. So in this case, we showed deformability of one Cauchy surface into another along some time-like curves, which are integral curves of a vector field. Well, keep extending your sigma prime further and further into the future, and then keep extending sigma further and further into the past. And you have basically set up a kind of foliation where sigma, being a-chronal, is topologically distinct from this time-like direction. And so topologically, the whole manifolds topology is nothing but sigma times the real line, going all the way from minus to plus infinity, because all these curves are taken to be inextendable. Okay, this is the idea. It's not a rigorous proof. If I were to do rigorous proofs, believe me, these lectures would stretch to 3 times the length at least. So, so it's not a rigorous, not meant to be taken as a rigorous proof, but it's cute, right? Because think of any example, you know, this is not red line as it seems to be written. It's real line, real line. So now topologically sigma cross R does not mean that the metric that as a differentiable manifold it's sigma cross R, because sigma cross R would be a manifold where, as a differentiable manifold, where the components of the metric G with one index in R and one index on sigma would have to vanish. That's not what we're saying at all. For that reason, from the metric point of view, nobody is saying that these are 90-degree angles in some sense, or that there's no component of these curves. But we're simply saying that it's topologically a direct product. And we know, of course, many examples. Look at the Schwarzschild black hole or whatever. Of course, the amount of the metric at any given point in space and time can depend on both space and time in detail, but the topological structure remains that of a direct product. Good. Any questions about this corollary? You see that after a little bit of hard work we did initially, things are falling out quite rapidly. I think we're getting a lot of good cute theorems. And finally, 6, I think this is what Krishna wanted me to prove, and I think now I can prove it. Sigma must be closed. This follows from the previous one, because sigma is the same as sigma times an arbitrary point in R, which I can just call the point 0. Okay, and 0 is closed in R, and this actually proves that sigma is closed in sigma cross R, which is M. So that's also done. Okay. I could get started on the next topic, I think, but I could also pause for questions, and we can just have questions. Well, let's see if there are questions. Questions? Did things get a bit easier today? I felt things became more natural once we got used to all this stuff. At least for me, I don't know about you. Yeah, this intuition of, corollary 6 is very interesting. Yeah.
Could you kindly explain this corollary 6? I'm not sure I got that.
6. Yeah. Give me a second. Actually, since we have all the time, let's look at what the boss says. So we are trying to prove that sigma is closed. So he says the following, page 18 of his light rays notes. Suppose that, so he first says, this immediately follows from the fact that M is S cross sigma cross R, since sigma cross 0 is closed in sigma cross R. Sigma cross a point. I think this is a general statement that in a higher dimensional space, a lower dimensional space cross a point. Okay, let's give then he gives a more direct proof. Suppose that P in the manifold is in the closure of S, but not in S. Okay, that would be an example where if S is not closed. Okay. Then he says, let gamma be any inextendable time-like path through P. It meets S at some other point P prime, since S is Cauchy. But then since P is in the closure of S, it is possible to modify gamma. Look, okay, I'm sure you can't follow what I'm saying. I'll draw his diagram that you'll follow. So here is sigma, the Cauchy surface. Here's P, which we assume to be a point in the closure of S, sigma, but not in sigma. Okay, so P is in sigma bar, but P is not in sigma. So we've sort of drawn it like this. So in a way, we've just picked a part of sigma that's missing. We've just drawn it so that P is allowed to be there. It's in the manifold, but it's not in sigma. Okay, and this would be possible if sigma was not closed, that you could have a point arbitrarily close to sigma without actually being in sigma. That's the closure I discussed earlier. Okay, now he says, consider an inextendable time-like path actually going through P. Okay, but now P is not in the Cauchy surface. So this time-like path has to intersect the Cauchy surface by definition of Cauchy surface somewhere else. So since it didn't actually intersect in P. So imagine I came along from here along this arrow, and I was looking forward to intersecting sigma in P, but I passed through P and I never intersected sigma. like a station that wasn't, or a point on the railway line which just didn't happen to be a station, or maybe it's better, it's a station which didn't happen to be on the railway line. Well, I'm guaranteed by Cauchy hypersurface and global hyperbolicity that this train must meet sigma anyway. So it obviously meets sigma here at P prime. Okay, but now P, okay, good. So now what I seem to have set up is a causal path, even a time-like path from P to P prime on the Cauchy surface, but it's not because P isn't in the Cauchy surface. But now all we do is take this path and modify it just like that. Okay, and it's always possible to modify this by just a little bit to skirt around P. And now this is a path, this path from here to here is causal, but it's not allowed because sigma is a-chronal. We are not saying that this original path, this one we are not saying gets modified. This path is an inextendable curve. It passes through P, but it hasn't yet reached sigma because P isn't in sigma. And so it meets sigma somewhere else. Okay, so this geometry sets up the possibility of drawing a curve from P prime, which comes arbitrarily close to P, and by slight deviation will hit sigma again, because P is in the closure of sigma. So it's arbitrary, any point near P is in sigma. That's what closure means, as we explained in the beginning. Okay, so therefore, sigma better be closed, because otherwise having points P which are in the closure but not in sigma would set up these causal paths from sigma to itself, which would contradict its a-chronality. Was that okay? Vivek, yes, the R in sigma cross R will be thought of as the time coordinate, exactly, because these curves, these integral curves which go back and forth between two Cauchy surfaces, are exactly how we imagine that some definition of time can be chosen. You see, we can't just draw straight lines and say that makes sense because it's a generic manifold with a varying metric. But as long as there are time-like curves, they provide a definition of time. Why can't I have an a-chronal circle in Minkowski space? Okay, I'm coming to that. First, did I satisfy corollary 6 people? I think Krishna originally asked me to prove that one about Cauchy surface being closed. Did I prove it? Okay, no objections. Now, Pawan, I did not understand corollary 4. J plus of P is closed for all P. A-chronal circle in Minkowski. How is it connected with corollary 4? J plus of P is the causal future of P. Not 4. Sorry, then which one? 3. I think you meant 3, Pavan. Yeah. And what the question is, why can't I have an a-chronal circle in Minkowski spacetime? Good. Because this theorem, which is a corollary of the previous one, would say that if I have an a-chronal circle, then from that circle, I can set up I think you're assuming something I didn't say. I didn't say that you can't have an a-chronal circle in Minkowski. I said you can't have if the Cauchy surface of that space-time is non-compact and connected. In some space I could have, but in any space where the Cauchy surface is non-compact and connected, then I can't have an a-chronal compact surface. And here I'll show you. If this exists and this also exists, then by this time-like integral curves construction, I can set up this thing. And I find that S prime must smoothly map to a subset of sigma, but there's no subset of sigma with the topology of S prime. That's the reason.
Sir, I have one question. So you said that if S prime is compact and sigma is non-compact, then this won't be possible. But since it's being mapped to a portion of sigma, isn't it not possible to have a compact portion of the non-compact sigma?
Okay. I think is a good question, Ritvik. I think the problem is that I'm doing an example where both are one-dimensional. Okay, but try to keep in mind that even if they are not one-dimensional, both are the same dimensional. And then it's not actually possible.
Okay.
So if it's one-dimensional, you agree with me, right? You might be thinking that, well, if this is a plane, then I can certainly map a circle smoothly inside a plane. But this and this have to have the same dimension. They are both hypersurfaces of codimension 1.
Okay.
So actually, yeah, exactly. Yeah. Okay. Pawan, I hope you are happy now. And Anish has a question. Any a-chronal surface can be embedded? Yes. Construct. What else do we need to construct sigma apart from the union of all a-chronal surfaces? No, union of all a-chronal surfaces definitely is not going to be a-chronal. I mean, remember, we can have an a-chronal surface here and another one here, right? I can't take the union of those two. That's definitely not a-chronal. So what we need is basically the fact that the Cauchy surface traps every backward going particle, if you want to put it that way, right? Or every future going particle that's in the past of the Cauchy surface better hit the Cauchy surface. It's really causality. It's really nothing more than that. It's the statement that the Cauchy surface really divides the manifold into future and past. Okay. So a-chronal surface doesn't necessarily do it. We did one example with the hyperboloid, doesn't work, and it doesn't divide effectively into future and past. You see, you could argue that in a way it does. Look at this hyperboloid. Okay. I could perhaps say that, well, the past of my whole manifold is everything here, and everything here and here is the future. It doesn't work because I can't predict the future in that case. Okay, and that's not acceptable. So that's why we want a Cauchy surface. So there's no general rule how to find a Cauchy surface or how to show that a manifold is globally hyperbolic. Rather, what we are doing is making a kind of restriction that when doing GR, we'll only restrict our attention to manifolds having a Cauchy hypersurface. Now, as I said right at the beginning, everything is provisional. So you might write a paper saying how to study GR in a manifold in a non-globally hyperbolic spacetime, and you might have some new idea. Can't rule out anything. So, but right now it's a provisional idea that we shouldn't include those at all, manifolds without Cauchy hypersurfaces at all in our study. And obviously people raise questions. Well, first of all, we are already, I think, reasonably happy that this rules out, I mean, all kinds of manifolds with a silly deletion of a point. I call it silly because if there's a point deleted, you can put it back, right? So why did you define the manifold to have the point deleted in the first place? There's unlikely to be any physics which makes you delete that point. So at least it rules out a lot of trivial examples. But a second point that people often raise is, well, I want to really do quantum gravity. I'll be summing over all spacetimes. Can you assure me that in the sum over all spacetimes, I'm not going to be including non-globally hyperbolic spacetimes? I don't know the answer. People debate it. It might still be true, though, because after all, when we do QFT on flat spacetime, flat spacetime is globally hyperbolic, and it remains globally hyperbolic even when we do the quantum version. But okay, in GR, the quantum version has fluctuating metrics, so we don't know. Okay, why is deforming? Yeah, Krishna had this question about this little cheat at the end. So the point why it's allowed is the fact that P is in the closure. You see, P could have been not in the closure of sigma. Sigma, we are assuming, is non-compact, and P could have been somewhere a mile away from it. Then this construction wouldn't do any good. Okay, but the fact that P is in the closure actually means that any infinitesimal deformation away from P lands you that is any little open set around P includes points on the Cauchy hypersurface. And that means that I can reach a point in sigma that is in sigma by a deformation, however small. Okay. And for example, if I've taken my curve here to be time-like, then a tiny deformation cannot make it space-like, arbitrarily tiny deformation. So that's the intuition. Okay, Sambit says 0, 2 pi can be mapped to the Cauchy line, but such a mapping might not be time-like. I don't think, well, that's the issue here, but how do you map a circle onto a line? There's no smooth map of a circle onto a line. The statement of topology that S1 and R are not homeomorphic, nor is S1 homeomorphic to any subset of R. Minkowski, the Cauchy surface is R3. Take a 3D ball outside this, and that is 2D sphere. Pawan, this is exactly the point. So even if I didn't say it, all these a-chronal surfaces are intended to be of codimension 1. I believe. I'll check. Proof of 6, yeah, perturbed it a little. Yeah, Sambit, maybe the diagram, I think my drawing, which is Vitten's drawing, is a little misleading. We are trying to argue whether sigma is closed or not. Okay, if sigma is not closed, there should be some point. If I could have drawn this diagram alternately like this. This could have been sigma. Okay, and P could have been here on its edge, and it would be more like this is a spatial circle, this spatial a disk in space, so at t equals constant, and imagine this as a 3D kind of drawing, and now my curve comes like this and fails to intersect sigma because it comes from below the plane of this drawing to above the plane of the drawing. Okay, and it goes through P, but P by hypothesis is not in sigma but in the closure of sigma. So that this curve doesn't intersect sigma when it passes through P. So there must be some topology by which it nevertheless passes through sigma at some other time, passes through actually a point in sigma. And now what we argue is that if P is not in sigma and Q is in sigma, and P is in the boundary is in the, in the closure of sigma, then any neighborhood around P has points in sigma. And one of those points, if I simply deform this line, then becomes a causal curve connecting this new point P prime to Q, and the achronality of sigma is gone. Yeah, it's fun stuff, it's very, very taxing. My God. I mean, I have never tried to teach such a difficult course. I'm not guaranteeing I'll succeed either. But so far, I think I'm sort of getting it, and I hope you are sort of getting it. If you are, then you are certainly doing at least as well as me, and I hope you'll even do better. So thank you all, and see you next time.